This is Phoenix A star. Phoenix A star is the largest black hole we've ever discovered, located in the Phoenix cluster, one of the most massive galaxy clusters known to us. This cluster lies about 5.8 billion light-years away from Earth. Imagine a black hole so massive, it defies everything we thought we knew about the universe. Phoenix A star isn't just any black hole. It's a cosmic behemoth with a mass of up to 100 billion times that of our Sun. That's like combining the mass of hundreds of billions of Sun-like stars into a single point in space. Compare that to Sagittarius A star, the black hole at the center of our Milky Way, which is around 4 million times the mass of the Sun. Nonsense, right? But how does something like this even come to exist? How does it grow so incredibly large? Short answer is, no one knows. But we have some clues. Accretion is a highly efficient way for black holes to gain mass. In the dense environment of the Phoenix cluster, there's plenty of material for Phoenix A star to feed on. The cluster is rich in gas and dust, which provides a continuous supply of matter for the black hole to consume. As this matter spirals inward due to the black hole's strong gravitational pull, it forms an accretion disk. The friction and collisions within the disk cause it to emit vast amounts of radiation, making the area around Phoenix A star extremely bright in X-ray and other wavelengths. Phoenix A star can also consume entire stars that venture too close. When a star gets within the gravitational reach of the black hole, it's torn apart in a process known as tidal disruption. The remnants of the star are then added to the accretion disk, contributing to the black hole's growth. Our Milky Way's Sagittarius A star supermassive black hole is relatively quiet, with much less accretion activity compared to the Phoenix A star, which is highly active and constantly feeding. Another significant factor in the growth of supermassive black holes like Phoenix A star is the merger of smaller black holes. In the crowded environment of the Phoenix cluster, galaxy collisions are relatively common, making it an ideal breeding ground for black hole mergers. When galaxies collide, their central black holes can merge, combining their masses. These mergers are not only significant events for black hole growth, but also for astrophysical research. They produce gravitational waves, ripples in the fabric of space-time that can be detected by observatories like LIGO and Virgo. Some scientists also speculate that such supermassive black holes might have started out with a much larger initial mass than typical black holes. In the early universe, conditions were different, and it's possible that Phoenix A star formed from the collapse of an extraordinarily massive primordial gas cloud, or even a cluster of smaller black holes. There's also a more speculative theory involving dark matter. Some researchers propose that interactions with dark matter, which makes up a significant portion of the universe's mass, could have played a role in the rapid growth of black holes, such as the Phoenix A star. If Phoenix A star has a higher efficiency in capturing dark matter, it could explain its extraordinary size. Understanding these mechanisms not only helps us comprehend the growth of Phoenix A star, but also sheds light on the evolution of other supermassive black holes throughout the universe. But Phoenix A star isn't just a cosmic heavyweight. It also has some unique characteristics that make it stand out from other black holes. Its exceptional luminosity. As it accretes matter, the surrounding gas and dust heat up and emit intense radiation, making Phoenix A star one of the brightest X-ray sources in the sky. This brightness provides astronomers with a wealth of information. By studying the X-rays and other radiation emitted by the accretion disk, scientists can learn about the properties of the black hole and the material it's consuming. Another unique characteristic of Phoenix A star is its impact on its host galaxy and the surrounding cluster. The energy output from the accretion process influences the gas and star formation rates in nearby galaxies. This interaction can regulate the growth of galaxies, a process known as feedback. Feedback from supermassive black holes like Phoenix A star is a crucial factor in the evolution of galaxies. The intense radiation and powerful jets of particles emitted can heat up and expel gas from the galaxy, preventing new stars from forming. This self-regulating mechanism ensures that galaxies do not grow uncontrollably. Phoenix A star also exhibits powerful jets and outflows. These jets are streams of particles accelerated to near the speed of light, launched from the regions close to the black hole. They can extend for thousands of light years, influencing the intergalactic medium and even affecting galaxies far from the black hole itself. But how have we been able to observe and understand this colossal black hole? Observatories around the world have played a crucial role in studying Phoenix Cluster. One of the key instruments in this discovery is the Chandra X-ray Observatory. Chandra has provided some of the most detailed images of Phoenix Cluster. By analyzing the X-ray data, astronomers can determine the temperature, density, and composition of the accreting material. This information is vital for understanding the physical processes at play in the vicinity of Phoenix A star. Radio telescopes such as the Very Large Array, VLA, have also been instrumental. They detect radio waves emitted by the jets and outflows from Phoenix A star. These observations help us trace the pathways of the jets and understand their impact on the surrounding intergalactic medium. This is a composite image that shows data from different telescopes. X-rays from Chandra depict hot gas in purple, and radio emissions from the VLA features jets in red. Optical light data from Hubble show galaxies in yellow, and filaments of cooler gas where stars are forming in light blue. These combined observations across different wavelengths and methods paint a comprehensive picture of the Phoenix Cluster. To study these regions, researchers also use computer simulations which model the behavior of matter in extreme gravitational fields, helping scientists predict future changes and compare theoretical models with actual observations. Studying these objects help us grasp the complex interactions that govern galaxy evolution